Hello everyone. So we are in the fourth tutorial class. So in this tutorial we will be studying gas ionization and breakdown mechanism. Basically we will be dealing with ionization potential, Townsend mechanism and Paschen's law. So we will be reviewing the summary of the things that we have learned first, and then we will do some numericals so that our understanding becomes concrete. So we start. So ionization potential, what it means actually, it is the energy that is required to remove an electron from a neutral atom. So that is the first ionization energy. And then if you want to remove a second electron from that, then that will be the energy that will be required is the second ionization energy. So the first ionization potential or the first ionization energy that is required is plotted in the graph that you are seeing in this in this diagram. What is plotted? The ionization potential in electron volt. So in the y-axis and in the z-axis, in the this x-axis, the z of the atoms in the periodic table. Basically, I have plotted for all of them. I collected the data and used a graphing software and plotted this. So these blue dots corresponds to the elements in the periodic table. So as I already explained in the class, the interesting part of this is that this is a zigzag kind of structure. Now, this zigzag thing originates because of the cell electrons distribution in various cells. When it is a inert gas configuration, the cells are complete and it is very difficult to take out an electron from the outer orbit. So that time the ionization potentials become very high, and the blue dots at the peaks, they all are basically referring to the inert gases. So this ion is as you are seeing, helium, then this 10 is neon, argon, krypton, xenon, radon, like that they are moving. Now in this actually you know several of the ionization potential very well. For example, the hydrogen, the 13.6 electron volt, we know since our school days that this is the ionization energy that will be required to strip out the electron from the orbit in hydrogen atom. Now the other very popular gas is the argon. So it is around say 15.6 electron volts. Somewhere here you will see this one is basically argon, and it is a very popular gas because it always allows you to form a very cool plasma with less instabilities, and above all this is a very cheap gas rather, and you will be surprised to know the concentration of your argon in atmospheric air, it is quite high. You can just check from the internet that the concentration of your argon is significantly high compared to other gases. Of course not, I am not talking about the nitrogen and oxygen. Other than that, rest of the gases, you can see that concentration of argon is significant. Now in this graph you notice that this 13.6 6 electron volt, hydrogen, and next one is helium. Helium is having inert gas configuration, so that is why its ionization potential is quite high, it is 24.6. Then you come the neon, and then argon, krypton, xenon, radon, like that it moves on, and the ionization potential get lowered because your levels are increasing. So orbit distance from the of the orbit from the nucleus, as it becomes more and more, the the influence of the nucleus becomes less, so it is easier to pull out the electron. So that is how the ionization potential goes. Now coming to the ionization process, this Townsend mechanism basically involves this ionization avalanche process, then breakdown in gas. If you want to initiate, the Townsend mechanism works there, and the electron multiplication under an electric field. So all this basically the part of the Townsend mechanism that happens when a breakdown takes place in a gas. Now this essentially addresses the ionization by electron collision. High energy electrons collide with the gas atoms or molecules, release more electrons, and those electrons participate in the chain reaction through the same mechanism, and finally you get an avalanche. Now in this scenario, we have already read in our classes that the Townsend's first ionization coefficient is defined as the number of ionizations per unit length by one electron. So this is how the Townsend's first ionization coefficient alpha is defined. Now numerically, in the expression for the ionization coefficient goes like this: alpha equal to A P exponential of minus B P by E. Here A and B are the constants for the gas, P is the pressure, E is the electric field. Now this constant A and B, they are dependent on the type of gas, the pressure and the electric field that we have applied there. Of course, these constants depend on the gas itself, and alpha basically depends on the pressure and electric field as well. Okay. So the constants A and B will be different for different gases. There are other ionization mechanisms other than the Townsend one, so I should note them in this tutorial. So ionization by positive ion collision, that is one. Then ionization by photons, that is called photoionization. So in the first one, ionization by positive ion collisions, positive ions gain energy from the electric field, and they can collide with the cathode. And in doing so, they can knock out electrons from the cathode, which are called the secondary electrons, and they can participate in the ionization process in the same way as the Townsend mechanism works. So this is ionization by positive ion collision. Then ionization by photons, this photoionization specially occurs in the UV or visible region with sufficient energy to ionize the gas. They are significant in high voltage discharge and pulse. So apart from this Townsend mechanism, these are the other two mechanisms through which the electrons can be generated, and these electrons later on can participate in the breakdown process through the same mechanism like the Townsend avalanche process. Now there are cathode emissions, which is very much important to make the plasma devices successful, and they are basically, you can say, thermionic emission, photoelectric emission and field emission. These are the three mechanisms by which cathode emission can take place. For the thermonic emission, you know the Richardson-Dasman relation that gives you the thermonic current density. Photoelectric effect you all know, so equal to h nu minus phi, and then this field emission is basically caused by the electric field that is existing in front of the cathode for the configuration of the device that you have developed. So, in all this case, electrons are getting contributed into the plasma, and those electrons can participate in the ionization process as they get accelerated by the existing electric field. Now, there was another important thing that we discussed was the panning effect. That was very interesting in the sense that role of metastable atoms in ionizing the gas was basically forming the mechanism. Now, what was there? You require a gas mixture, like in neon you are introducing an impurity of argon, and it is the metastable levels of neon which are having a energy level much higher compared to the ionization energy that is required by argon, and when the electrons are getting re-excited from there, the lines, the photons that are getting emitted from there, they are sufficient to ionize the argon. So, this effect is the panning effect, and metastable states contribute significantly in this mechanism. Now comes the contaminants. They usually lower the breakdown voltage, like moisture. They are available in most of the gases unless you take special precaution, so they can lower the breakdown voltage. Then if your surface, the metal which you are having, they can have some contamination, they can increase the surface emission sometimes, and all these can affect the pass chain breakdown curve, which you have read in a regular class. Now impurity, that plays a very important role in cathode emission. I will tell you one thing, tungsten is having a work function that is more than 4 electron volt. When you introduce just 2% of thorium oxide in that as impurity, the ionization potential, that not ionization, that work function gets lowered below 3 electron volt. So, that is the power of this impurity in lowering the work function of material which is supposed to emit electrons. So, impurity plays an important role. Sometimes they are very beneficial for the electrodes to emit electrons. And now I switch to the pass chain law. This is a famous pass chain breakdown curve that you all know. So, what is the specialty of that? That breakdown voltage depends on product of pressure and distance. Okay, it is not pressure alone or not the discharge gap alone. So, it is a function of the product of PD. P is the pressure and D is the discharge gap. As you are seeing here, this VB is a function of PD. No here P is occurring alone or D is occurring alone, they are occurring as a product PD. So, this breakdown voltage is a function of the product, pressure and distance. And you know that this curve is non-linear. If you plot VB as a function of PD, you will find a minima, and all experimentalists and technologists, they always want to exploit or they want to use the minimum of the pass chain breakdown curve, so that you can get the breakdown applying a minimum high voltage. So, that on either side of the PD mean the breakdown voltage increases, on lower side because the pressure is low, so you have fewer number of collisions, and on the right side, upper side, P is high, So the mean free path is less, so they are not gaining sufficient energy unless you increase the electric field, that is you increase the applied voltage for a given gap. So that is why the breakdown voltage increases on either side. Now what are the applications and implications of this Paschen law that we have studied in our class? That they are very important when we are considering the discharge in gas discharge tubes, then in high voltage engineering, plasma devices, and lightning and spark formation. So now we come to one actual problem where we can use the theoretical understanding that we have gathered from our regular class. So here the problem is posed like this. For a gas with the gas constant A equal to 15 centimeter per centimeter and B equal to 365 volt per centimeter torr, we want to calculate the Townsend fast ionization coefficient. That is, how many number of electrons will be produced per length. Here you note that we are using the units like centimeter and torr. So they are basically working units in this area, and if pressure is equal to 1 torr and electric field is 1 kilovolt per centimeter that has been applied. See, 1 kilovolt we are talking, you need a high voltage for the breakdown to take place. Then for that, what will be the alpha? That is, number of electrons or number of ionizations that will take place per centimeter. So here we go, actually alpha, the expression we have just put, A P exponential minus B P by E. Okay. Now the constants that has been provided here, A we put over here, P is 1 torr, we have applied here, and then exponential minus B P by E. So you see that this unit of this B should be like this, volt per centimeter torr, so that you know this this whole quantity becomes dimensionless. Got it? P is torr, so this torr will cancel and the numerator will be in the form volt per centimeter, and that is just the unit of the electric field. So they get cancelled and you get a dimensionless quantity within this argument. Okay. So what you finally get? 15 into 1 into exponential of, you put this value, then you are getting 10.41 per centimeter. So we can say that at least 10 ions are generated per electron per centimeter in the process of ionization through Townsend mechanism. So you note the values for which we have just introduced this problem, that per centimeter you are getting some 10 ions per electron, you remember that, and the number of electrons that are being produced from the cathode, they can be anywhere, say 10 to the power 18, 10 to the power 19 per meter cube kind of thing that are getting generated from there. So you can understand that those will be multiplied by around 10 as they proceed by just 1 centimeter. So you can understand how small the 1 centimeter is. So it is just tens of millimeter. That is the way the electrons are getting multiplied by the Townsend mechanism. Now there is one other fact, is that what we have got, the 10.41 per centimeter. Now you know that this many number of electrons are getting generated. We understand that 10 electrons will be generated or 11 electrons will be generated, but how is 10.4? 0.4 electron is what actually? So we should understand that this figure is coming because of the statistical nature of the problem. Okay, like that, you know, it may be once 10 electrons and next time it may be 11 electrons. It may even be more than 11 or it may be even less than 9 sometimes. And when you take a large number of such measurements, and make an average, then this number is coming out. So it is not that you are getting half of an electron or 1.5 of an electron, not like that. You are getting the full number of electrons, either it is 10 or 11 or 9 kind of thing. But when you are doing a large set of measurements and taking the average, therefrom this fraction is coming. So this is also signifying the statistical nature of the problem. So from this problem in this tutorial, we understand the kind of electrons that can be generated per electron if it just proceeds by 1 centimeter. So we remember that. Then we come to another problem. So there we will be directly doing with the that Paschen breakdown curve. For air, in that Paschen breakdown formula, A is 112 per centimeter, B is 2737 volt per meter, and gamma is given 0.01, and we want to know the breakdown voltage that will be required for a PD of 0.5 torr centimeter. So the problem is clearly defined. For air, we have been given the constants A, B and gamma for air, and we have created a discharge setup where the PD is just 0.5 torr centimeter. We want to know the breakdown voltage. So we come to the breakdown formula. So VB is BPD by log of APD minus log of 1 plus 1 by gamma. So we put the values. So this quantity we are evaluating here and is giving 4.025 using the values that has been given, and this quantity log of 1 plus 1 by gamma, this is coming like this and it is giving 1.529. So we just directly calculate the VB. It is coming to be B, that is 2737 into PD, which is given 0.5, and at the bottom the quantities we have already evaluated. So it is 4.025 minus 1.529, and you are getting a breakdown voltage of 548.3 volt. Okay, so it is not even a kilovolt that you are requiring. So I would be happy as a plasma experimentalist if you are asking me to give a some 548 volt, not a kilovolt. I'll be quite happy. But you note that the obtained breakdown voltage is obtained for a 5 millimeter gap when your pressure is 1 torr, and that is quite low pressure where you are going to get this breakdown. But if you really want to get it done at 1 atmospheric pressure, then you need to actually apply a much higher voltage for the breakdown to happen. This is this PD is whatever we have put over here, some value is there, 0.5 same torr. So D is you are keeping suppose fixed. Then if you increase the pressure, your breakdown voltage increases, because now you are reducing the mean free path. So unless you apply a much higher voltage, you will not be able to impart that much energy to an electron as it travels the mean free path, so that it gets sufficient energy to cause ionization. So that is the reason. So this tutorial problem gives you a direct idea about how to calculate the breakdown voltage once a gas is given and the parameters required to evaluate the breakdown voltage is known. Okay, so that is how now you are getting some hand-on experience about the breakdown voltage in this tutorial, and in the previous tutorial you have got an experience about calculating the Townsend's first ionization coefficient. So with this I stop this tutorial session and we will meet you in the next tutorial in the next week. Thank you.